Wanted to work through an example that involves calculating a electric potential and electric field of an arrangement of point charges. So it's an example that involves knowledge of the electrical potential and the electrical field of a point charge. It's an example that involves working with superposition principle, which works for electrical potentials and electrical fields. It's a work that illustrates an important difference between electrical fields and electrical potentials. It's an important practical difference. There's an important physics difference too, is that electrical potentials are scalar quantities. They're represented by just a number. It can be positive, can be negative. Electrical fields are vector quantities. They have a direction and a magnitude or a strength. And so that's a fundamental difference that's important when superimposing electrical fields versus electrical potentials. So let's work through this problem. We've got three charges. They're all plus Q. They're all the same size and the same sign, and they're located at the three corners of a right angle, of an equilateral triangle. That's a triangle with 60 degrees in each of the corners. And we're asked to figure out the electrical field, the electrical potential at the center of the triangle. I've denoted here the distance to the center. I've called that A. That's the distance from any of the three corners. It's the distance from each of the three charges to the center. So let's start by calculating the electrical potential V, and then we'll go on and calculate the electrical field E. So the potential. The potential at the center of the triangle, due to the three charges, is the superposition of the electrical potentials of the individual charges. So V1 is the potential of charge 1. I call that the charge at the top of the triangle. V2 is the potential charge 2. I call charge 2 the one on the right of the triangle. And the potential 3, that's the potential due to charge number 3. That's the one on the left of the triangle. So this is superposition principle. And this works relatively easy here because these three potentials are scalars. We can just add them up like numbers. So if I'm going to solve this part of the problem, the potential due to charge number 1 is going to be KQ over A. Q is the charge, it's creating potential. A is the distance of the field point from the potential, and K is the Coulomb constant. And then same thing for the two other charges. Each of those contributes a KQ over A. That's because each of them has the same charge. Each of them's at the same distance. So they all contribute equal potentials. And so if I add these three contributions up, I get 3KQ over A as the potential at the center of the triangle. Now, I should say, because only potential differences are physically significant, that this is the potential difference with respect to zero potential infinitely far away. So when I said that the electrical potential of a point charge is KQ over the distance from the charge, that expression for the electrical potential is under the assumption we're calling the potential zero infinitely far away. And so our calculation is under the assumption that we're calling the potential to be zero, very far away. And so 3KQ over A is the potential where there's 0 volt potential, a large distance from the triangle. Okay, part B is to calculate the electrical field at the center of the triangle. To do that, I'm first going to add to my sketch of the arrangement of the charges and the geometry of the problem. I'm going to add to the sketch the fields of the charges Q1, Q2, Q3. I'm going to draw vectors representing the fields of the charges Q1, Q2, Q3. So let's start with Q1. It's above the field point. It's a positive charge, so its field will be vertically downwards, something like this, away from that positive charge that's creating that field. I'll label that E1. The field due to Q2, it's both to the right and below the field point. The electrical field created by charge Q2, I'll call it E2, looks like this. It's pointing away again from that charge located at this corner, the right-hand corner of the triangle. And then the third field, that's due to charge number 3, I'll draw that too. Again, that's a positive charge. The field will be radially outwards from that positive charge. It's going to look something like that. Now, label that E3. Now, there's a couple of things that are very important about these 3 fields, E1, E2, E3. One thing that's important to note that will help us is that the size of E1, E2, E3 are all the same. So they're all created by the same size charges. They'll all correspond to a field point that is an equal distance A from those 3 charges. So all these fields have the same strength. So I'll write that as that E1, its size here, its magnitude here, equals E2, its magnitude, its size, equals E3. And I'll just call that size, I'll just call it simply E. So the sizes are all the same. The other thing that's important is on this sketch, I know the directions of the 3 fields. So obviously, for charge number 1, the field is downwards. Charge number 2, the field is at 30 degrees above the horizontal. The triangle in this corner of the equilateral triangle is 60 degrees. Since the field is at the field point, that's halfway around this 60 degrees. So it's directed at 30 degrees. Same argument applies to the third field. Its angle to the horizontal is also 30 degrees because it too lies along a line, a radial line that bisects a 60-degree angle now in the left-hand corner of the triangle. And so that's the geometry. So we actually know, without any calculation whatsoever, a lot about the sizes of the fields, that they're all the same. We know the directions of all 3 fields from the geometry of the problem. So the general way in which you add up vectors, like these 3 electrical fields, is by first breaking the vectors down into their horizontal, vertical, or X and Y components. Then you can add up all the X components just as if they were numbers, kind of like potentials. And you can add up all the Y components just as if they're numbers, again, like potentials. And then that gives you the resulting X component, Y component. Once you've got the resulting X and Y components, if you'd like, if you need them, you can figure out the magnitude of the resulting field. That's by Pythagoras. You can figure out the direction, the angle of the resulting field. That's by a little trigonometry, and normally the tan function, the arctan, inverse tan function. So let's go ahead and make those steps. The first one is to write down the X and Y components of the 3 vectors. So let's start with 1, vector 1, due to charge 1. I want E1x and E1y. 1 is the label for the charge, X and Y are the labels for the horizontal, vertical components. It's easy to see what these 2 components are, consulting our sketch, consulting our picture. The field is vertically downwards. So there's no X component. It's all in the downwards X direction. I'll call that the negative direction. The field is is minus E in the X direction, Y direction. And so that's the first charge. What about the second charge? Second charge, we want E2X, E2Y. These are the X and Y components for the second charge. Well, let's look at the vector for the second charge. It's pointing up and to the left. So to the left, I'm going to call to the right the positive direction. To the left is the negative direction. Up, we've already called that the positive direction because down was the negative direction. So we're going to get a negative and a positive component respectively for these two. For the horizontal component, you see it's adjacent to the angle of 30 degrees. So the horizontal component is cosine of theta times the length of the vector E2. So this is going to be E cosine 30 degrees, whereas the vertical component, it's opposite the triangle. It's over here. And so it is extracted from the hypotenuse, the electrical field strength, using sine theta. And so that's going to be E sine 30 degrees. And so that's the components of the second field, E2. We got the final field, E3. So we want E3x, E3y. For E3's X and Y components, the X component is in the positive X direction, and the Y component is up, so it's also in the positive direction. So both of these are positive. And the X component is again obtained by the cosine of the angle times the field strength. So cosine 30 degrees times E. And the Y component, which is the vertical side of this triangle of the field and its X and Y components, that's obtained because opposite the angle, that's obtained by E sine 30 degrees. So now we got the components of the three vectors. That's the first step in adding up these three vectors. So next step is to find the X and Y components of the resulting vector. And to find the X and Y components of the resulting field, we just got to sum up the X and Y components of the individual fields. So for the X component, we've got to add up E1x, E2x, E3x. For the Y component, we've just got to add up E1y, E2y, and E3y. So what's going to happen here? Well, let's think about the X component first. We've got 0. And then we're going to add a minus E cosine theta. And then we're going to add a plus E cosine theta. The minus E cosine theta and the plus E cosine theta will cancel. The 0 is already 0. So these components add up to 0. So this is 0. What about the Y component? What happens when we add these up? Well, we've got a component that's minus E. And then we've got two components that are plus E sine 30 degrees and another plus E sine 30 degrees. E sine 30 degrees is half of E. It's E over 2. So we've got two positive E over 2s and a minus E. And so these cancel out. Minus E plus E over 2 plus E over 2 is also 0. So EX and EY, the resulting electrical fields X and Y components, are both 0. And so the vector E, that's 0, 2. So there's 0 electrical field at the center of this arrangement of charges. We might have guessed that. There's a kind of symmetry in the arrangement of charges. One on the left, one on the right, one upstairs. And because of that symmetry, of the arrangement of charges, both their sizes and the directions to those charges, it wouldn't make sense for the field to have a component left or right or up or down. And so that this fact that the field is 0 is a reflection of asymmetry in this triangular arrangement of these charges. Anyway, that's a problem that involved the electrical potential of a point charge, the electrical field of a point charge, the superposition of electrical fields and electrical potentials. It involved addition of potentials, which is adding up numbers. It involved addition of fields, which is adding up vectors. It involved geometry. We had to lay out the charges. We had to understand the directions of the fields. We had to break fields down into their components. So it also involved trigonometry. In the end, we found a simple value, 3kq over a, for the potential at the center. And we found a very simple value for the field at the center. It's 0.